But let me check if we can like stop sharing edit. I don't see. Yeah, I can't see any options for pin. So yeah.
To turn the camera off, you mean?
Yeah.
I think that the host would the setting who's talking the live.
Yeah, we can ask people to turn the camera off when we start, maybe. Actually, I think you can stop. If you right click on the name of the person, there should be something like stop webcam sharing.
Mm-hmm. Yeah, but just let the people if they want to, I guess.
Yeah.
So we can see everyone. Okay, so just 12 minutes left. Yes, Pankaj, yes, you can share the meeting link with your friends, of course. So it's for free. You can invite your friend. Thank you very much. All right. So it's 1 minute before 13 UTC, and people are coming in. So we'll start in 1 minute, in about 1 minute. You may share the meeting link to your friends. So yeah, feel free to send. Otherwise, we're also online live in Facebook. So you may also use Facebook Live for our discussions or for interactions today. Right, so it's 13, exactly 13 UTC. So welcome participants to our second IAU Inclusive Astronomy Outreach Community of Practice webinar. So this is our webinar number 2. So if you are new, so welcome, and if you joined our last webinar, and welcome again, and thank you for participating in our webinar and in our networking
Ora si
session.
registrerà la conferenza.
Okay, so by the way, we will record this webinar so that we can post it in our YouTube channel as well. Also to open your camera so we can see your beautiful faces. All right, so this webinar is all about tools and resources for astronomy. So we have 3 presenters or 3 presentations today. So number 1 would be Dr. Kimberly Arcand of NASA's Chandra X-ray Observatory. And then the next presenters will be Ferdinandino and Luciano Garamon from Italian Amateur Astronomer Union. And the last but not the least presenter would be our lead for the IAU Inclusive Astronomy Outreach subgroup, Mr. Cesare Pagano. So without let's continue with our presentation number 1. So hi, Ms. Kim. So Dr. Kim. So presenter number 1 is Dr. Kimberly Arcand, visualization scientist and emerging tech lead of the NASA's Chandra X-ray Observatory. Dr. Kimberly Arcand is a leading expert in astronomy visualization and an innovator in 3D imaging, printing, and extended reality applications with astrophysics data. She has worked for NASA's Chandra X-ray Observatory at the Smithsonian Astrophysical Observatory since 1998, and her current research includes sonification and spatial data, screen-based hologram, and other intersections of emerging technology and astrophysics. So I will give now the floor to Ms. Dr. Arcand. All right, so.
Wonderful. All right, you can see my screen okay? Wonderful. Well, thank you. It's so lovely to be here with you this morning for me, this afternoon, or this evening for you, whatever the time zone might be. I'd like to talk a little bit about my work that I've been doing for NASA's Chandra X-ray Observatory almost 25 years. I've been working on the data from the telescope for quite some time, and I think for the past, I don't know, maybe the first 8 or 9 years of my career, I was really interested in just trying to figure out how to work with these X-ray photons, these X-ray packets of energy and information. And mostly that was through visuals, like what's on my screen now, which is the image of the supernova remnant, Cassiopeia A, which we're seeing mostly in X-ray light in this beautiful expanding degree of hot gas and material. But it did occur to me that I was missing an entire segment of the population by only presenting this information as a visual, as a 2-dimensional image. And we started working with some colleagues at MIT, mostly Dr. Tracy Delaney, who was working to create the first 3D model of this data set, Cassiopeia A. And that 3D model really got me thinking that perhaps we could do something more with our data than just create a flat 2D image. And so I think once that happened, it really got me thinking about this information in a whole new way. And this on my screen now is just a short video of what that three-dimensional model of CAS-CPA looks like. So this was using the data that we understood was moving away from us versus which was moving towards us to be able to create this three-dimensional model. Now, around the same time, Smithsonian, who were in the process of 3D scanning and then 3D printing President Obama's head. And I thought, well, if they can make a 3D print of President Obama's head, I could surely figure out how to make a 3D print of this exploded star. And so that's what this image on the current slide is showing. It's a still photograph of that three-dimensional print of this CAS-CPA supernova remnant. And once that happened, I really started thinking, all right, well, who take advantage of these three-dimensional models? So we started working with the Federation of the Blind and some of their summer students in order to really test out 3D models before CAS-CPA, figuring out that these 3D prints were really helpful for explaining some of these scientific concepts, for helping people explore the data using their own tactile techniques. And what we found was that they really did need help. These are the lessons learned that we've been able to glean from so far. When it comes to 3D printing these objects, the size of them really does matter. If you can make a larger 3D print, it allows more detail for those topographical nuances to be able to be explored. The resolution of a 3D printer is important. When possible, being able to have a higher resolution print allows for smoother and better 3D models. For sure, making sure these prints are very strong. If you have jets that are thin, if you have weak points where something might sort of attach very loosely, any sort of joints or other weak areas, making sure that you reinforce them is also really helpful. And then also something that became very, very quickly apparent to us is that we were approaching these 3D models from a sighted perspective, but when the students who are blind or low vision approached them, they were coming from their own perspectives, and there were very simple things that they wanted to know more of. So for example, with CAS-CPA, the data from the outside shell tells you one story, but inside the shell tells you another story. So of course, it made sense to actually cut that 3D print in half so that that could be explored both internally and externally. But overall, the result was that the students wanted more 3D models. They wanted more content that could be explored tactilely. And what we found over the past 10 or more years with this project is that it wasn't just benefiting users who are blind or low vision, it was also benefiting other learners as well, children's, adults, it didn't matter. It was just a lot of people found being able to explore a space object with their hands, to be able to feel it, even though it's a tiny, tiny, tiny scaled down version and in plastic, was really helpful. So we've done things since then, like work on using magnets to be able to attach models that are cut in half. We've created a kit of these materials that we test piloted through the IAU, through UNESCO activities, through the various NASA centers. I've got a photo of one of those test kits on the screen now. It's showing about 6 to 3D printed models of different kinds of stars in various stages of evolution. Stellar nurseries, stars that are maturing, stars that have exploded, stars that are hanging out together in pairs, and some of the tactile and braille materials that go with them. So we've been growing our 3D printable library of objects ever since that first exploration of that exploded star, different kinds of exploding stars, different kinds of young star systems, stellar binaries, and the like. And what we found too is that it takes a long time to create a true 3D model. You have to have really good data. You have to have that blue shift and red shift information. You have to have, really solid evidence to be able to create that 3D model using the observational data or substituting with simulational data, mathematical models in the absence of pure operational data. And so in the absence of always a lot of new models, what we decided to do was adapt Dr. Nicholas Bond's software. He is an astronomer in the UK, an observational astronomer who's blind, and he created this software to be able to create tactile relief map plates, essentially 3D printable plates, objects that are just in 2 dimensions, that still has a relief texture so that you can explore the topography of that data, if you will, through various different kinds of energy. So that project was going well and good, but then the pandemic hit, and because it was impossible, we lost access to our 3D printers, our students that we were working with. It just became challenging. And so at this time, my colleagues and I started thinking about how we could pivot, and that was more of a rapid response project that was completely digital. And I had been dabbling already in sonification, which is this information into sound through use of an audio of whatever kind. And this is a field that's a very large field of research. Many astronomers and other kinds of scientists, many different kinds of researchers are actively sort of pursuing this. It was inspired by Dr. Wanda Diaz and her PhD thesis. So we started doing these sonifications with my colleagues at System Sounds, Dr. Matt Russo, who is an astrophysicist as well as a musician, and his partner Andrew Santaguida, who is a musician and like sound engineer. And we started attacking X-ray data through this new method. So how can we take this data that starts out invisible to humans, by the way, right? No one can see X-rays natively with human eyes. So why not think about other ways to perceive this data, for other ways to represent this data than through sound or some other means? And here I'm just going to play one example sonification file, where this is the Chandra Deep Field South. The image itself is perhaps not super exciting to look at. It's a black rectangle with some multicolored dots kind of like strewn throughout it. And though the image itself might not look exciting, the science is. This is a deep field showing like thousands of black holes, essentially. This beautiful, dense population of black holes deep, deep, deep in our early universe. And to me, that but when you look at the image, perhaps it doesn't come across. However, when the sound is mapped using a mathematical translation of the pixel data to sound data, what we have is the following. There, but what's happening too is essentially a sweep of the image from the bottom to the top of the data, and all of those dots, those black holes, or those active galaxies with supermassive black holes at their cores, they are all different energies according to the different object that they are. And so we've cut the sound by those energies, whereas the lower energy X-rays are being represented by the lower sounds and the higher energy X-rays by the higher sounds. So you're hearing the difference in all of those energy levels as you scan up, and you're hearing it through a stereo sound. So I don't know if the stereo sound can be communicated through this platform, however, that's the idea. And so it's just a completely different way to be able to express the scientific information. To me, makes a lot of sense. When I first heard this one, it was very moving for me because, again, this is a very exciting image scientifically, but perhaps does not evoke much excitement if you don't know exactly what it is that you're looking at. But when you hear it, it provides a different kind of experience of that data. And when you hear that you're listening to these little beeps and boops of thousands of black holes, perhaps that might be a little bit more exciting. So these sonifications have sort of taken on a life of their own. Back in August, we had a viral moment, I guess you would say. One of our sonifications of the Perseus cluster of galaxies that has a supermassive black hole at its core that is sort of belching out these wonderful bits of energy that are causing sound waves in the hot gas around it. We took that sound wave and sonified it, and that went much more viral than we would have ever expected. I'll just play a short clip of some of the results from the news stories. But according to our meltwater metrics and statistics, about 2 billion people were potentially reached based on the market values of all of the different press and media vendors and venues that carry the bridge. So here is a little clip of that.
Get ready for this, everyone. The actual sound of a black hole. Not the literal sounds from the cosmos, but a translation to help blind and low vision people appreciate the majesty of space.
Chandra astronomers use NASA's flagship X-ray telescope to sonify sound waves.
What we're listening to is essentially a re-sonification, so a data sonification of an actual sound wave.
That really reaches inside, doesn't it?
So again, we had absolutely no expectation of the sonifications being this well received, but the fact that sighted users as blind and low vision users were all taking such pleasure and excitement from this way of understanding data was very, very just completely enthralling for me. I just was so happy to know that people really responded to this data in such a cool way. Again, very unexpected. So since then, we started again with this project back in 2020, and we now have a collection of over 20 different sonifications. They're bespoke creations that we're creating by hand to really help represent the scientific information. And we're using like Python and Logic Pro to be able to do that. But we've also been creating on the side some additional platforms, if you will, for very basic real-time sonification in a very simple manner, just a one-to-one ratio of pixel to data sound, simple, that the user can do on their own, as well as an application that students can try to understand and learn how to do some of the coding on their own to create their own sonification. So this project that started out as a rapid response to the pandemic has completely taken on a life of its own. It's been the most popular feature on the Chandler website since 2020, pretty much. Huge chunks of 2021 and 2022 that have just taken over our web stats. Pretty much anytime we post these on the NASA social media accounts or other digital platforms, they do very well. Significant media coverage, as I mentioned. But we did a research survey of this idea of studying the perception and response to these sonifications across the expert to non-expert spectrum and across sighted users and blind and low vision users. And we had about 4,500 responses, which I am still in the process of analyzing because it was way more data we're expected to get. But overall, we had really high learning gains and enjoyment levels for both groups. But we did find that learning about access for the sighted group was significant, meaning that they understood in some new way that other people are accessing information differently than they are. And I think that was pretty exciting to see. So I'll show you a few quick glimpses of some of the research data, but hopefully I'll be finishing up the article sometime this year. Again, I mentioned that we're in the process of creating additional types of ways of understanding and exploring through the sonification, such as this app with my students. Very excited to be able to do that, but there was one project missing. So back at the end of 2020, I worked with some colleagues, JJ Hunt and Christine Malik, who are professional visual describers. And Christine is a member of the blind community. She's been blind since birth. And they have this fantastic podcast where they describe a lot of science data sort of live in real time with these rich descriptions to help other people understand what's happening. And we started to create these rich visual descriptions for every Chandler image that we release to the public. And we've been doing that since January of 2021. Whether it's an image, whether it's a time-lapse movie, a sonification, or an illustration, we provide this rich text in text format and audio format, also as a podcast and on like XML feeds. The technique of this has been pretty important. We have a few things that we did through both trial and error and then also user testing. One, that just describing the image as you might describe a piece of artwork on a museum wall was not as satisfying. There had to be some explanation of the scientific phenomena and what was happening. What the visual viewer was seeing sort of needed to be looped in with what the scientific understanding was, at least in a general way. But that integration was really important. The second was that the style of those descriptions was really important. This type of information can be sort of overwhelming for non-scientists if it's not presented in just the right way. So being careful to write with a style that was approachable, using short sentences, numerous commas, always being careful to use those proper nouns versus using it or, you know, some other sort of more casual word was really critical, because as you're building up a mental map of something, when you're listening to a lengthy description through a screen reader, for example, the commas give you pauses to help absorb the information. Less complex sentence structure lets you focus on the content and not the sort of dripping across of all the information. And that frequent use of proper nouns, meaning referring always to Chandra versus it, was really important to be able to keep all of that information straight. So what we did find is that this information and this technique has actually helped us all over the place. So I'm going to read very quickly just a short snippet of one of these rich visual descriptions. This is on the Cat's Eye Nebula, which is sort of like if you could glimpse into the future of our sun in, say, 5 billion years or so, we might have something to look at, something like the Cat's Eye Nebula. And so the description goes like this. The Cat's Eye video features a static image of an ethereal shape surrounded by concentric circles. The shape is the Cat's Eye Nebula, a huge cloud of gas and dust blown off of a dying star. The concentric circles are bubbles expelled by the star over time. The dust cloud resembles the translucent pastry pulled to golden yellow points near our upper right and lower left, with a blob of bright purple jelly inside the bulbous pale blue core. So the idea is to really provide something that has meaning, but that also adds value to a user who's going to typically be non-sighted. But as I mentioned, we found these other improvements. So by taking our captions and thinking about how other users are actually reading them or listening to them as they're being described over a screen reader, it's actually improved our work overall. Our search engine optimization has improved because by using more proper nouns, by constantly referencing things like the object name or the Chandra name, it has actually improved our search engine optimization. They've also helped improve our social media and our HTML. We've been metadata tagging them in addition, and it's just sort of improving our products overall. So I can just say that when we've done some user reviews of this material, the 3D models, the sonification, and the visual descriptions, they've all done very well, but the visual descriptions are the one that most blind and visually impaired users specifically call out as being the most important, because it is an immediate real-time result as they're exploring through all the plethora of information available on the web to be included in NASA Science as it's being released with a description that's made just for them, that's tested with people who are blind or low vision, has been really important. So the other products are wonderful and I will still keep doing them, but being able to have that sort of real-time response, I think, has been very important to our community members. So I'll just sum up in saying that, you know, when we're designing the universe and we're thinking about how to help others understand all the fascinating bits and pieces of our universe, that availability of data does not equal accessibility. It does not equal equity of the data. We really have to think hard and better on how to do that. And just finally, my last slide is just major props. All of my colleagues, the visual description team, the sonification team, the 3D team. It's been a really fun experience getting to explore our universe in all of these different dimensions and with all of my fabulous colleagues. So I just have to give a shout out to everybody there. And yeah, I'd love to take questions at this point. Hopefully I didn't speak too long. I think I went 2 minutes over.
That's fine,